This conference will now be recorded.
Yes, good morning everyone, whether it's audible online. Yes, online students, whether it's audible. Yes, very good morning. Right. So today we are here to discuss on physical design demo. Right. So today our agenda is to discuss on why physical design. Right? What we do in physical design. What basics required to do to work on physical design. PD. Right. Next, how the course, how the course is, how the course works, right? Like on what day we are going to conduct the course. So we are going to discuss these four objects today. Yes. I think now it is audible, right? So whether it's audible now?
Yes, sir.
Yes.
It's audible, sir.
Yes. Sir. So physical design is back-end flow of ASIC design. So before seeing why physical design, right? First we will understand what is Foundry. So Foundry, what is Foundry? So Foundry is a place where IC is fabricated. Foundry is a place where IC is fabricated. So we are going to fabricate IC in the foundry. Right? So this is called as IC, integrated circuit. This foundry can understand only GDS2 file. It cannot understand anything. Foundry cannot understand RTL. Foundry cannot understand netlist. So Foundry can understand only GDS format. Right? Foundry can understand only GDS format. Only GDS format. So for that reason, what we have to do is, what is GDS? GDS has layout information. GDS has layout information of cells. So what is layout? If you want to understand what is layout, right? So if you take one inverter, so you should be having this basic CMOS basics. So if you don't have CMOS basics, we are even offering that is in basic course. Right? If you take a CMOS inverter, this is the schematic. schematic diagram of CMOS. This is V in, this is V out, this is VDD, this is ground or VSS. This is a schematic of your CMOS inverter. But layout means, so layout has, this is source, this is drain, this is gate. So layout is nothing but a top view of your CMOS. Right? Top view of your CMOS is called as what? Layout. So if you have this CMOS, right? CMOS has first P substrate. CMOS has P substrate. So inside this P substrate, you are going to create N well. Inside P substrate, you are going to create N well. In N well, you are going to fabricate this PMOS, right? You have PMOS source and drain in N well. PMOS source and drain. This is P plus region. On top of this, you have silicon dioxide. On top of this, you have polysilicon. This is gate. This is drain, and this is source. Or I can call this is source and this is drain. Anything is fine. This is your PMOS. So PMOS is fabricated in N well. This is P substrate. And your NMOS, right? You have NMOS. NMOS is fabricated here. NMOS is fabricated here. NMOS, you have source and drain. This is N plus region. And you have silicon dioxide. On top of silicon dioxide, you have polysilicon. You have this connections. This is drain. This is gate. Right? This is source. So here drain and drain is shorted. Here this is drain and drain is shorted. This drain and drain is shorted. And this is your V out. And similarly, your gate and gate is shorted. This gate and this gate is shorted. And this is your V in. So source of your PMOS connects to VDD. And the source of this PMOS I can connect to what? VDD. And this source of your NMOS, this connects to VSS or ground. So this is your CMOS structure. So for this, right, if you draw the layout, layout is nothing but a two-dimensional top view. What we see from top view, two-dimensional top view is called as what? Layout. For this CMOS, if I draw the layout, so the layout will be like this. So this is your P substrate totally. In P substrate, you are going to form N well. This is your N well. This is N well. And we have diffusion, P plus region, and we have N plus region, right? So if I cross polysilicon or P plus region, right? So this forms a transistor. This here. This is your drain, and this is drain, right? This is the drain of your PMOS. This is a P plus region. This is a P plus region. This is source, and this is drain of your NMOS. This is source of your NMOS. So this is P plus region, and red color is polysilicon. This is poly. Because when you see from the top, right, only poly is visible, only source is visible, only drain is visible from the top if you see. And similarly PMOS also. You know, when I see from the top, only drain is visible, source is visible, and gate is visible. So that is what we have here. This is also poly. And here I have VDD. Here VDD rail. Here we have VSS rail. VDD, VSS we have. So we have to short drain and drain here. You see here, drain and drain is shorted. Drain of your PMOS and drain of your NMOS, both are shorted. So you short a drain and drain by using metal layer. This blue color is metal layer. So drain and drain is shorted. Then gate and gate is shorted. Right? Gate and gate is shorted through polysilicon. So short through gate and short your gate. Short gate and gate. And source of your PMOS is connecting to VDD. Right? Source of your PMOS connects to VDD. And source of NMOS connects to VSS through metal layer. These are all metal layers. This is your VDD. This is VSS. And for polysilicon, I can give, right? I can give the metal connection for polysilicon. And for the drain and drain short, right? Even I can give the connections. Here there is a contact cut. Contact cut means whenever your polysilicon is connecting to metal layer, you have a contact cut. This is your V in. This is V out. So here red color is polysilicon. This pink color is your P plus region. And blue color is metal layer M1. This is also M1. This is two-dimensional top view, right? It is two-dimensional top view of a CMOS. Null top view of CMOS. So my foundry can understand only this layout information. I was discussing about this why foundry. So my foundry can understand only GDS. What is GDS? GDS is nothing but what? Layout information of cells. So GDS doesn't have any schematic information. GDS doesn't have any symbol information. It has layout information. This is the layout. Layout is nothing but a two-dimensional top view. If you see the MOSFET from the top view, right? Whatever visible, polysilicon is visible, source and drain is visible. Here also, right? Source and drain is visible, N-well is visible here, and P substrate is visible. So that structure is called as layout. It is layout of CMOS. So my foundry can understand only layout information, right? So our role is to give the layout information to the foundry. That's it. Physical design engineer's role is give the layout information, create the layout information, whatever we get from synthesis tool, and give that to foundry. That is what works. So physical design comes one step before the generating GDS file. After physical design, generate the GDS file and send to foundry. Right? So to understand exact role of physical design, we have to understand ASIC design flow. To understand exact role of physical design, we have to understand what is ASIC design flow. Why we go for physical design. Ultimate step of all the design is last you create GDS file. GDS has layout information of cells and connection between cells and give this layout information to the foundry. The foundry will manufacture IC for you. This IC. They will manufacture IC for you. So that is what the ultimate requirement from the design engineers. Now to understand exact role of physical design, right? We want to discuss on what is ASIC design flow. ASIC design flow what is ASIC? ASIC stands for, what is ASIC? Yes, application specific integrated circuit. So we are building a circuit specifically for particular application. It is not for general application. We are developing an IC specially for particular application. So it is called as ASIC. So ASIC design flow, right? It has following step: specification. So secondary starts with RTL RTL coding. Third is functional verification. We are mentioning only major steps. In between, we have plenty of steps like linting. We have RTL integration. We have clock domain crossing checking. All right. We have gate level simulation. Right? So we are mentioning only major steps. So after that, we have synthesis. Then we have design for testability. Then we get what? Physical design. After physical design, right? Sign off checks. So the steps for ASIC design flow. After sign off checks, right? Generate GDS file and send the file to Foundry. Generate GDS file and send file to Foundry. So these are the steps in ASIC design flow. So our role is just before the file sending to Foundry. So we are the last step before file sending to Foundry. If I want to design any IC, we are in the design flow. We are not in the fabrication. So fabrication happens only in what? It happens only in the Foundry. We are entire all the steps are only designing the IC. Right? Because why we have to design IC, right? IC should, the main reason is IC should work. IC should work properly. So second thing, IC should operate with highest speed. Highest speed. IC should consume less power, and IC should have less area, and third thing is IC should be in a point. So whatever design, right? Whatever design we have, design should be in a design should be fabricated properly without any problem, right? So we have to give the design in form of GDS2 file to the foundry so that it can be fabricated properly without any problem. Right? It is called as a design for manufacturability, right? DFM, design for manufacturability. We have to give the design in form of manufacturability. So I cannot give the GDS2 file which cannot be fabricated. So it should be in a position for fabrication. So we have to do the design, means we have to do ASIC design flow by meeting all these parameters. See, without any parameter, if you do the design means it is very easy, right? Doing anything without constraint is very easy. If there is a constraint like go to VLSI Guru and come back with 20 rupees, right? That is difficult. If you don't have any constraint, then book a cab, come here, go back. Very easy. So doing anything without the constraint is very easy, but with the constraint is very difficult. So we have to design an IC to meet all these parameters. It's role of every team, not only physical design. Yes, sir. So to understand why physical design, to understand this, we have to little bit go through the steps of ASIC design flow. How the step is in what step what is done. We'll understand. Then only we can understand why physical design. So specification. So IC specification. IC specification generally top team will be involved. Right? They will get a specification of IC. What is area of IC required? Right? Area, speed of operation, right? Estimated speed of operation. Functional blocks. So what functional blocks should be present in IC? So average power consumption or battery. What is the battery capacity? What the battery they are using? What is the battery capacity that leads to average power consumption? All these things, the specification is taken from the top team and with the help of architectural team. And that information, what are all the functional blocks required, right? What are the functional blocks required? That information is given to RTL coding team. They will start coding the each and every functional block. RTL coding team, they use Verilog or VHDL. Verilog or VHDL for design entry. For design entry, they use Verilog or VHDL. So my question is, why only Verilog or VHDL? Why they are using Verilog or VHDL? Why not schematic? Why they are using any programming language to describe the circuit? To describe any circuit, why we have to use any programming language? I can directly describe a circuit with help of schematic, right? Okay, I can describe a circuit like I have, for example, I have a mux. Mux means, okay, you have one AND gate, right? One inverter you take that you give to one step, another AND gate. This is A pin, this is, or this is I naught, this is I1, this is select line, right? So output of these two you give to one OR gate, alright? This is Y pin, right? This is equivalent to mux. So why I have to write the RTL program? Why I cannot describe in the form of circuit? This is also mux, right? This is mux. This mux why I have to describe in RTL program? Why I cannot describe in form of schematic or why in form of symbols? Because the general rule is, right, remembering the internal structure is very difficult, but we can remember the behavior. Right? So truth table, from the lower classes we study the truth table. So truth table is nothing but the behavior of a circuit, how the circuit behaves. So implementing that behavior is easy, but implementing the circuit is difficult. So human cannot do that. He can do for simpler circuits. For bigger circuits, he cannot do that. But implementing the bigger circuits with respect to its behavior is very easy. For example, if you want to implement bigger circuits, right, you can implement by using what state machines. I have state machines S naught, I have state S1, I have state S2, right? I have state S3. Like you have a ATM machine, right? it will be the reset state always. If card is inserted, it will go to S1 state. Card is inserted means 1. If no card inserted, logic 0. It is in the previous state only always. So S1 state means pin entering state. It is pin entering state. If pin is entered, right, go to next state. 1 means pin is entered. If pin is not entered for 5 minutes, then go back to what state? Reset state. And you are in S2 state, means pin is entered. Right? Then enter amount. If amount is entered, go to cache dispatch state. If amount is not entered, right, go to reset state. If cache, after that cache dispatching, right, here only one option, right? After cache dispatching, if cache is dispatched, go to reset state. If cache is not dispatched, means if the sufficient amount is not there, uh, give the output message that you don't have sufficient amount. After that, go to reset state. If cache is not dispatched, also go to reset state. After cache dispatching, also go to reset state. Like that, right? Entire total behavior of a circuit, I can first form small state machines. Then implement the state machines. Implement one state machine. So now, this is a behavior of a circuit. So implementing behavior of a circuit with respect to RTL coding is very easy. We cannot implement directly the what structure, but behavior is very easy. For example, you take your right D flip flop. If I ask how many can you tell the internal structure of D flip flop by using basic gates, hardly few can tell it. Right? But if I tell what is the behavior of your D flip flop, right? Your D flip flop has clock, it has reset, it has a D pin, right? It has Q pin. Clock you have, reset you have, D you have, Q pin you have. If I tell what is its behavior, if I ask what is its behavior, right, the behavior is very simple. You have a reset pin. Right? Reset is asynchronous reset, a reset pin. If reset is 1, logic 1, output is Q is always 0. If reset is 0, right, Q is going to take D at what edge? At the positive edge. At positive edge, Q is going to take value of what? D. This is a behavior of D flip flop. You can easily implement this by using if statements, right? If reset is equal to 1, right, your Q is going to take what? 1 tick binary 0. Else your Q is going to take what? D. So this is called as behavior of a circuit. This behavior can be easily implemented by using programming languages. So for that reason, what they did is at the beginning, so implementing a complex program is very difficult by using a structure. First we start implementing by using a behavior. So we use the concept of C++, how they are implementing the behavior. We also use that concept. We will implement any circuit by using behavior, like this behavioral modeling. So you can use if statement, you can use case statements, you can use loops. All these are supported in Verilog. So by using all these things, you can implement the behavior of a circuit very easily by using RTL. So for that reason, right, at the beginning, so you can ask a question, Pratik. Yes, Pratik, you have raised your hand. You can ask a question. Okay. So we can enter to the design easily through Verilog or VHDL. The advantage of using Verilog or VHDL is we can describe the circuit Describe circuit based on behavior. Right? I can describe a circuit based on its behavior easily. That is the advantage. That is the reason why we start with RTL coding first. Right? So we can use if statement, we can use loops, we can use case statements, we can use procedural blocks like always blur. We can describe a circuit. Whatever you're telling, please tell me clearly. I'm not able to understand. Whatever described from initial starting, what is this? Yes, I am in the beginning step only. Right? You don't worry. I started only with ASIC design flow. We started only with ASIC design flow. See, please follow the steps. Any of this video will be given to you. Right? So what I started is IC integrated circuit is fabricated in Foundry. This IC, right? We are not going to fabricate that. The IC is fabricated only in Foundry. So Foundry is not, most of the foundries we don't have in India. Most of the foundries are situated outside the India, like TSMC, Taiwan, Japan, right, China, and USA. Most of the foundries are situated outside India. For foundries, we have to give the GDS field. See, he has left the meeting. He has asked the question and he has left the meeting. Oh, he is there. Okay, fine. Most of the foundries, right, is outside the India. For foundries, we have to give GDS file. GDS file consists of layout of a design. Right? This is called as layout. Top view of a CMOS. Right? Top view of a CMOS is called as layout. GDS consists of a layout of a design. Two-dimensional top view of CMOS is called as layout. So this information Foundry is understanding. Only this information I have to give. So this is one inverter. Right? This is one inverter. For example, this inverter is connecting to some other cell means for that cell I have to write the layout, right? And I have to make the connection. Output is connecting to input of this cell. So the layout of a cell and its connection, right? This information is present in GDS file. This GDS file we have to send to the Foundry. So Foundry can understand only GDS file. In GDS file only we have layout of a cells and its connections. We don't have any other thing. So this is what the Foundry understand. That is what I started. This is what the Foundry understand. Foundry will understand only GDS information. So that is the role of physical design team to generate the layout and its connection between cells. To generate the layout and connection between cells, that is a layout. That is a role of physical design team. CMOS, we will do the basic course here. First of all, what is required for the course, right? We'll do it. The basic course we'll do it. Neil West you can refer. Or Pucknell is there. David Pucknell. For layout, you can refer that. If you don't have CMOS basics, right? We will do CMOS basics here. We'll start with digital CMOS, TCL. That I'll discuss, right? And even that is also our agenda. What basics required for physical design? I'll discuss that when time comes. So we have to give this information. Then what is input for physical design? So to understand that, we are going to understand what? ASIC design flow. What is the role of physical design engineers? To understand this, we are going to what? ASIC design flow. ASIC design flow starts with what? Specification. So specification of IC. Specification means what? Specification of IC. Oh, Pratik, you got it? What I did at the beginning? Whether you got it? I just told Foundry can understand only GDS information and GDS has layout information. Then we will see how what physical design engineers, what inputs they will get and what they will convert to layout. That we'll discuss. What information they are going to convert to layout. Now RTL. So I was discussing about RTL coding. Why we describe any circuit? Why we describe any circuit through Verilog or VHDL? The main reason for that is yes, here only, right? After E, the physical design steps comes. We have physical design after DFT. That I will discuss now. So RTL. So RTL, we describe many circuits only by RTL because RTL, by using RTL we can capture what? Behavioral information. We can directly describe the behavior of a circuit. I need not to worry what is the structure of a circuit. For that reason, I can use RTL. But this RTL, whatever I have, Verilog code or VHDL code, I cannot give to Foundry. Foundry will not understand this. Because now design is in the behavioral form in the RTL. Right? Design is in the behavioral form. So after RTL coding, you have functional verification. What is functional verification? Verifying functionality of a design. Verifying functionality of a design is called as functional verification. Now design is in what form? Behavioral form. In the form of Verilog or VHDL. It is in the behavioral form. This behavioral form design, I have to verify it. How to verify it? By applying test cases. By applying test cases. By applying test cases. Test cases means so you have behavioral, right? Apply reset as one. Right? For first apply reset as one. Observe what is the output. After that, make reset as what? 0. Then apply D as 0. Observe what is the output. At positive edge, I should get what? Q as 0. Now apply D as what? 1. Right? Then at the next positive edge, I should get Q as what? Logic 1. So apply different inputs and observe what is the output you are getting. If you are getting intended output, what you want, then your functionality is met. You are applying this inputs to this design only. The Verilog program only you are going to apply. Because there is a software called as simulators, they will allow you to apply the inputs. And by using a simulator, you can also see what is the output. By applying different inputs, if you get the intended output, then your functionality is met. Right? That is called as functional verification. So verifying functionality of a design by applying test cases is called as what? Functional verification. Test cases means different inputs, different combination of inputs. If you want to verify you are written the program for AND gate. So how many combinations input you will apply? 0, 0, 0, 1, 1, 0, 1, 1. Applying different combinations of input and verifying the output, what output you are getting for this combination. That is called as functional verification. The functional verification is very easy for smaller designs, but complex designs it is very difficult. So to understand, to work on this functional verification, right, you should be understanding system Verilog. You should be knowing what is system Verilog, and you should be knowing what is UVM, Universal Verification Modeling or methodology. This separate course. This course is called as design verification course. We had demo yesterday, right? So to understand that, you should be knowing Verilog, system Verilog, and UVM. Verilog, system Verilog, and UVM. Then what is difference between Verilog and system Verilog? So in Verilog, most of the constructs or most of the commands what we have, that is synthesizable. But system Verilog is not synthesizable. It's just to do what? Functional verification. Right? In system Verilog, what are the commands you have or the constructs you have? That is not synthesizable. That is just to do the functional verification. That's it. To do functional verification, so you should be knowing Verilog, system Verilog, and UVM. Yes, you will do by using test bench only. That is what test bench. Apply different inputs through test bench. Right? Test bench means what? Waveforms. So here my reset is 1. What is output? Output is 0. After that reset is 0, right? What is output? My Q is going to take what? D at only positive edges. So generating the waveforms like this is called as what? Test bench waveforms. So you are going to do functional verification by generating test bench waveforms only. That is front end part. We are not bothered about, but only we should understand is the design is in what form? Behavioral form. This behavioral form design, my foundry can't understand. Next, I have to convert into a circuit level or gate level. For converting a behavioral form design to gate level, we have synthesis. Synthesis is nothing but convert RTL code to gate level netlist. Convert your RTL code to gate level netlist. That is called as synthesis. Now behavioral form you converted to what? Gate level form. So whatever the RTL you have written, right? Whatever the RTL you have written, RTL program, that you are converting into gate level program. Gate level diagram, I can tell. This. They are converting to gate level diagram like this. This is RTL. So it is step by step process, not a sudden process. Right? Behavioral convert to the circuit level. This is behavioral form. Convert that to circuit form. Convert to what? Circuit. So synthesis is very important step for physical design. So I want to ask one thing. So we are converting this behavioral to the circuit level. So who is going to give the circuit, or who is going to tell what gates I should use to form the circuit? I'm using some gates, right, to form the circuit. Then what gates I have to use? There is a tool called a synthesis tool. The synthesis tool will convert RTL to gate level netlist. We are not going to convert it. Probably all the UG students have already done by using Xilinx. They have converted this RTL program to gate level netlist or by using any tools. Then who is going to tell what cells I have to use here? Okay? That is very important for synthesis. Sir. So for synthesis, what are all the inputs to do synthesis? What are the inputs? Inputs for synthesis. Yes, one of the input is RTL, right? is RTL. This RTL coding. It is a VRL form. That is .v. .v means it is Verilog program. Verilog or VHDL. .vhd. One is RTL. One of the input is RTL. Second, what is I think required? See, my synthesis tool is converting this design to RTL to the gate level circuit. But this gate level circuit information I have to give, right? What gates I have to use to form the circuit? What are the gates I have option to use? Right? So that information is present in a file called as liberty file or library file. So next is liberty file. Liberty file is called as .lib. The extension means the file extension. Before I can be having any name, after that the extension is what? .lib. .lib is nothing but your liberty file. So in liberty file, we have standard cell information. So what information we have? Timing and power information. Timing and power information of cells. Timing means the delay of a cell. How much time it takes? Delay of a cell. So what is meaning of standard cells? All the gates, right? Basic gates like your AND gate, OR gate, NAND gate, NOR gate, XOR gate, MUX, flip flop, D flip flop, right? Flip flop means what type of flip flop? D flip flop, um, inverter, buffer. So these are all called as what? Standard cells. So these basic cells, right? Any circuit, to implement any circuit, these are called as standard cells. They are called standard cells because the height of a cell, height of all the cells are almost same. Height means the height of a layout. I want to say, right? This height of a layout, height of a layout, this height of a layout, this height of a layout for all the standard cells are same. So for all the standard cells, timing and power information is present in .lib file. For all the standard cells, what information? Timing. Timing means delay of the cells, right? Delay, delay of cells and power. How much power it's going to consume each cell while working, right? You have different types of powers again. Leakage power, switching power, short circuit power. All those things we will discuss in PD basics and even in physical design also. So delay information and power information of all these cells is present in a .lib file. A .lib file is called as liberty file. Then my question is, who is going to generate this file, liberty file? Who is going to generate this liberty file? See, we are not going to generate liberty file, right? The liberty file is generated by a PDK team, process design kit team, right? Or the team is called as library characterization team. There is a separate team called as library characterization team. So they are going to develop this. So see, I'll just give a small introduction about library characterization. Right? What library characterization team will do is nothing but they will get the spice models from Foundry. Right? The library characterization team, they are going to develop this liberty file. Right? They will get library characterization. This library characterization team, they will get spice models from Foundry. So what do you mean by spice models? Mathematical model for MOSFETs. See, MOSFET means it is a silicon, pure silicon. It's implemented in the silicon. Whatever behavior it is showing in silicon, that for that behavior we should use a mathematical model to capture that behavior. Right? For example, I walk on average, right? I walk 10 steps, right? For 1 minute. Then how many steps I will take for single second? Right? That is like mathematical behavior of my speed. Like that, I have to create a mathematical model for the MOSFETs because MOSFETs can give its operation only they are implemented in silicon. But how to model them in the software? These models we are using, these spice models we are using in software, right? So we have to use spice models. Spice models we get from Foundry. The spice models they will take, and by taking spice models, right, they will draw the schematic of each and every circuit. Like this is a circuit of what? Inverter. Right? They will draw the schematic of each and every circuit. They will apply different inputs and they'll connect different load capacitance and they will calculate what is the delay and they'll calculate what is the power consumption and they will give it in a file called as what? .lib file. They will draw the circuits for all the circuits. Inverter, NAND gate, NOR gate, for all the circuit, all these gates, they will draw the CMOS circuit and they will calculate delay and power consumption and they will give it in a file called as .lib file. These spice models will differ from foundry to foundry and technology to technology. Right? Foundry means the place where we get our IC fabricated. It changes from foundry to foundry, and it also changes from technology to technology. Means, for example, for same foundry, the spice models are different for 14 nanometer, and the spice models are different for 7 nanometer. Spice models are different for 28 nanometer. What do you mean by nanometer? 14 nanometer means what is the meaning? We call technology, right? 14 nanometer technology. What is the meaning if we have 14 nanometer technology? 14 nanometer technology means the distance between source and drain, right? This distance between source and drain is how much? 14 nanometer. Here, right? Distance between source and drain is 14 nanometer. Seven nanometer means the distance between source and drain is 7 nanometer. Channel length or distance between source and drain is called as what? Technology. All the gates, inside gates we have source and drain, right? The distance between source and drain is 14 nanometer only. So now library characterization team will give the dot lib. That dot lib we are going to use in synthesis and physical design. Right? This is the role of the library characterization team. So there is one more team, standard cell layout team. There is one more team called the standard cell layout team. This is a separate team. It's not a physical design or it's not part of synthesis. So their role is only to draw the layout for all the standard cells. For all the standard cells, they are going to draw this layout. Right? This is called a standard cell layout team. Layout team. Right? So input for standard cell layout team is schematic. Right? What are the schematic they have drawn? Library characterization team. That is the input. Schematic is input. Schematic is input. They will take the schematic and they will draw the layout. Right? That layout they will give in a file called as a LEF file and GDS file. GDS file for each and every cell. It is not for entire design. It's for each and every cell. They'll give the GDS file because layout can be stored only in two formats, only GDS format or LEF format. So GDS stands for graphical data stream. LEF stands for layout exchange format. Layout exchange format. For all the standard cells, they will draw the layout. We are not going to draw the layout. Physical design engineers, there is a separate team called as what? Standard cell layout team. And that layout information is present in which file? LEF file or GDS file. But still, we should be having a knowledge of layout. Physical design engineers. Because we are working on layout, but we are not drawing layout. We are using the layout which is already drawn by standard cell layout team. So they will give the layout in form of GDS or in the form of LEF. So we use LEF. That we will show you. Anyhow, see, we have complete industrial project. When you enroll to the course, anyhow, we are going to work on those files only for 3 months, 3 to 4 months. So we are going to show you real LEF, real dot-lib. GDS is not a human readable format; it's ASCII format. Only Foundry can understand it. What? It is in a binary format. It's in a compiled form. We cannot. No individual can read GDS. Only tools can read GDS. Only algorithms can read GDS. But LEF and dot-lib, it is a human readable form. We can understand it. Anyhow, we are going to show that all the files. When the course begins, right? We are going to show. So now for synthesis, what is important? The second thing is what? Liberty file. So in the Liberty file only, we have information of what? Standard cells. These standard cells are what? These standard cells are mapped to technology. Mapped to technology means these standard cells will vary if the technology changes. Because if technology changes, spice models will change. Right? If spice model changes, the dot lib will change. I can tell that this dot lib is dependent on technology. So third input for synthesis, logical synthesis. What is third input for logical synthesis? The third input for logical synthesis HTC file. HTC stands for synopsis, design, constraints file. So in this file, we have timing constraints. Here we have timing information. Here we have what timing constraints. So timing constraints means my design should work within this clock frequency. Right? Mainly here we are going to specify clock frequency. So here we are going to specify. No, it is not standard design constraint. It is a timing constraint mainly, right? Timing constraint means clock frequency. It is synopsis design constraints only, right? But the cadence tool provider, they don't want to use the word synopsis. But this STC commands first used by synopsis only. It is synopsis design constraint only. But some other tool provider, for example, the other tool provider, Mentor Graphics, if they are using these commands, they don't want to use word synopsis. They have changed the word to standard. But actually, it is synopsis design constraints only. So mainly here we can give what clock frequency, and here we can give many inputs. If I tell also you don't understand that, you will understand only if you enter into the course, right? You have set input delay, set output delay, set driving cell, right? Many constraints, many timing constraints we can give here in HTC file. So main thing here is clock frequency. I have to synthesize my design to meet this clock frequency. That is difficult. Do synthesis means it's very easy. Converting RTL to the gate levels, to the gates present in a standard cell is very easy. But converting RTL to this gate level, right? By meeting this constraint is very difficult. I told you, right? I gave an example. If your parents tell that go to VLSI Guru and come back is very easy. Book a cab, come here and go back. But if there is a constraint like go within 20 rupees, is very difficult. So we have to synthesize in such a way that we are meeting this clock frequency. So for that we have a check called as a setup time check. Setup check. Setup timing check. Whether my design is meeting this clock frequency or not, right? To verify that we have to set up timing check. That check we have to do. So these three files are very important for synthesis to happen. So my RTL is converted into gate level netlist by using cells present in what? Liberty file. Then what do you mean by gate level netlist? What is the output of synthesis? Output of synthesis. Yes, good, right? Output of synthesis is gate level netlist. .v again. Gate level netlist is also .v. RTL is also .v. Gate level netlist is also Verilog program. RTL is also Verilog program. Then what is the difference between both? So RTL is in the behavioral form. Gate level netlist is in the structural form. First difference. RTL can use any constructs like if statement, case statements, procedural block, assign statement. But gate level netlist should be having only gates. What are the gates we are using? Gates and its connection. Only this information should be present. Apart from that, we should not be having any other statement like if statement, case statement, assign blocks, assign statement, or procedural blocks like always block. None of things should be present. Only you should be having gate and its connection. That will be present in RTL. Sorry, that will be present in gate level netlist. So in gate level netlist, only we have gates and its connection. See, I'll give you one example. You take this example. See, this is the what a gate level design. What is this gate level design? What we got after synthesis, right? And this is OR gate. The OR gate name in library file, Liberty file is R2. R2 means two input OR gate. The AND gate, this AND gate name in Liberty file is AND2. The inverter name in Liberty file is INV, just INV. So Liberty file has different things again. It is having different drive strength, different threshold voltage cells. So that we'll discuss later. All those things. But now the name of OR gate is R2, name of AND gate is AND2, name of inverter is INV. Yes, we can generate. See, we can generate a GTech. We can generate a GTech netlist. GTech means within the synthesis tool only we have one more library file that is called a synthetic library file. See, this library file is technology dependent library file. Externally, I am giving it. Synthesis tool only will come up with one library file, internal library file. All the synthesis tool will be having it. That is called as GTech files, generic files. If I don't give this external file, Then tool will convert to the cells of that file, internal GTEC file. See, the first step is first it will convert to the internal file, internal cells, then it will convert to the cells present in Liberty file. Synthesis is two-step process. One is first RTL you convert into generic cells. Generic cells are the cells present in the library file of synthesis tool. Next, those generic cells convert to what? Cells present in the Liberty file. If you don't give Liberty file, you should start only with the unmapped design. If you get this, this is called as map design. That is what a doubt you had. See, that we will do it later. See, because it's just a demo class, right? Even the UG class students will be attending. So just I'm going on the top level. I cannot go into the depth. That we will cover in the synthesis class. You will be having 2 to 3 days of synthesis class. There we'll cover. In physical design only we'll cover that. So synthesis is a two-step process. To be very things right. In two-step process, first your RTL, whatever RTL you have, that it will convert to unmapped design. Unmapped design. Unmapped design means here every synthesis tool will be having its own internal library. That is called a generic library. So tool will first convert your RTL to the GTEC cells, the cells present in generic library. That is called as GTEC cells, means general technology library. Then this unmapped design will map to what? The cells present in Liberty file. That is called as map design. Map design. So map design means here all the cells will be having the cells present in which file? Liberty file. So standard cells will be used present in Liberty file. So if you don't give this file, you should stop synthesis here only. Okay. How to write netlist for this? What is netlist for this? Gate level netlist. I told you, right? Output of synthesis is what? Output of synthesis is gate level netlist. For example, in your design, you only have 3 cells. Generally, we will not be having 3 cells. We will be having millions of cells. Means more than lakhs of cells will be present in a design. So how to convert what is netlist? So netlist has same thing, right? Like RTL, you will be having module name. I can give any one module name. I'll give it a stamp as a module name. I will be having inputs and outputs of a design. What is inputs? A, B, C. Output is Y. Then declare inputs and outputs. Inputs are A, comma B, comma C. Output is Y. And intermediate signals. This N1 and N2 input or output. These intermediate signals are called as wires or nets. Right? So I should declare that as wire. Intermediate signals are declared as wire. Wire N1, comma N2. This is also Verilog program. Correct? But here in this netlist, right, I will be not having any behavioral description. I will be having only gate and its connection. That information is present. How it is present? First, first we will describe the inputs and outputs of your OR gate. Right? So R2. R2 is a library name of your OR gate. So along with that, my synthesis tool will give one instance name. This instance name of this OR gate is U1. This instance name of your AND gate is U2. The instance name of this inverter is U3. Why this instance name is given, right? For every cell there should be a unique name. I can be having even one more OR gate, or I can be having 10,000 OR gates in a design. But every OR gate should be having unique name. So for that unique name, synthesis tool will give this unique name. R2, U1, right? Next, you will be having port mapping. Port mapping means dot of A1. Dot of A1 means for A1 pin, For A1 pin, what you are connecting? What you are connecting for A1 pin? A, right? Port A. For A2 pin, right? Dot of A2. What you are connecting for A2? B. Right? For A2 pin, we are connecting B. Dot of Y. Y pin of your OR gate. What you are connecting? Net N1. Right over. Next, we will describe AND gate. Right? What is the library name of AND gate? AND 2. And my synthesis team will give one, synthesis tool will give one instance name. That is what? U2. And what we are connecting for A1? Dot A1 of N1 means for A1 what is connected? Net N1. For A2 what is connected? Port C. Dot A2 of C. And for Y pin what is connected? Net N2. Right? And last cell. What is last cell? It's inverter. Its library name is inverter. The library its name is inverter. So what is the instance name? U3. What is the input? Dot A of N2, comma, dot Y of this. Dot Y of output is what? Y only, right? Y. Next N2 module. Only this information should be present in your netlist. Cells and its connection. So only just this netlist if I give, whether my synthesis tool or some other tool can identify the connection between cells. Yes, right, because this N1 net is output of what? OR gate, and this N1 net is input to what? A1 pin of your AND gate. So here connection is established, correct? Any tool, if I give only this net list, right? My tool can identify the connection because N1 net is output of what? Y, and it is input for what? A1 pin. So connection is present here. Here also, right? N2 is output of what? Y pin, and this N2 is input to what? Inverter A pin. So connection is established. So this is called as, so my netlist should be having only gate and its connection. Apart from that, none of the Verilog construct is not allowed. Anything like assign statement, like procedural blocks, or if statement, case statement, loops, nothing is allowed. Only should be having cells and its connection. But connection is present here, right? N1 is output of your OR gate and it is input to your what? A. So connection is established. So this is called as netlist. Right? Now, after synthesis, my design is in what form? It has one level of hierarchy is reduced, right? From behavioral, we are reduced to gate level. But synthesis is not straightforward. It's not like simply give the files and obtain the gate level netlist. To do synthesis, I have to meet all these things. After synthesis, we have many checks, right? That those intermediate teams I'm not mentioning. So we have checks like timing check, setup timing check, whether timing is met or not, whether functionality is met or not. In the gate level netlist, right? Functionality is met or not. So we will do logic equivalence check. This netlist we compare with RTL. We do logic equivalence check or formal verification we'll do. Means RTL and netlist both are implementing same functionality or not. That we'll check. Then we'll check whether this gate level netlist is having our description of circuits or not. Right? Like we'll do some netlist check. Netlist, for example, now this netlist should not be having any ambiguity. Ambiguity means I have one cell driving other cells. This is fine. right? One cell driving other cells are fine. Output of this cell can be taken by other cells. If this is producing logic 0, all these cells will take what? Logic 0. One cell driving many load cells. This is called as driver cell. This is called as what? Load cell. Driver cell driving many load cells are fine. But many driver cells driving one load cell is not possible. This is not fine. Because now there is ambiguity whether this cell should take input of this cell or this cell. So multiple drivers is not fine. It means this cell is having multiple drivers. It is driven by multiple cells. Multiple drivers are not fine. But one driver can drive multiple cells. That is okay. This is an ambiguity, right? This is ambiguity in the netlist. If you have this type of things in the netlist, right, it's not correct. So all these checks we have to do. After doing all these checks, right, we will forward this to DFT. So DFT means design for testability. Output of DFT team is also netlist, the same netlist. But what the DFT team will do is, so DFT team will add additional logic. They'll add additional logics to the design without affecting functionality. Without affecting functionality. DFT team will add additional logics to the design without affecting functionality. Why they are going to add? Can anyone tell me why they are adding it? So whatever functionality my gate level netlist is implementing, right, that is not disturbed. Without disturbing this, they'll add additional logics. Logics means additional gates. They'll add to the design. Why? Because see, my chip is fabricated. My chip is fabricated. I want to test the chip whether it is fabricated properly or not. There is a more probability that the chip may not be fabricated properly because fabrication is chemical driven process. It is not a mechanical process. I have a metal layer. This is a metal layer, complete metal layer. I want to get only metal layer in this process, in this portion. I want to get metal layer only in this portion. In all other portion, I have to remove the metal layers. In all other portion, I have to remove the metal layer. So what I will do is this portion where I want to remove, where I have to retain the metal layers, right? That I'll cover by oxide layer. This I'll cover by what? Oxide layer. And by using mask, right? I'll cover by oxide layer. Other regions I will treat with the high concentrated acid. Other layers will etch away, right? Because I'm treating with high acid, right? These layers will etch away. These layers will not etch away. Right? These layers will be as it is. So other regions I'm going to remove. See, if I tell the foundry to create metal layers only in this region, my foundry cannot create because my foundry is working in nanoscale. My foundry can create a bigger metal layers first. Then wherever it wants metal layer, right? Only in that region they will retain the metal layers by using mask. So this is they will cover with mask. Right? This they will cover with mask like this. Wherever I want to retain metal layers, right? They will cover with mask. Cover with mask. Cover with mask. Remaining regions you treat with high concentrated acid. So remaining regions metal layers will be removed. Only in this region I will be having metal layers. Every layer is fabricated like this only. They cannot fabricate only polysilicon here, right? They will be using polysilicon everywhere. Only in this region they are going to retain, other regions they are going to remove. That is called as etching process. For etching process you require a mask. Any of this fabrication process you are going to learn. So now why I am telling this is chemically driven process. So what happens is when metal layer is fabricated, They may not be fabricated in a planar structure. They may be fabricated like this. I'm talking in nanoscale. Nanoscale means 10 to the power of minus 9. In scale, whatever you see is 10 to the power of minus 3, the lowest division of your scale. So nanoscale means 10 to the power of minus 9, my metal layer can be fabricated like this. Here acid is not worked properly, so both the metal layers are shorted. Even Foundry cannot identify this. The metal layers are shorted means even Foundry cannot identify this. Because in a IC we will be having millions of, means 10 lakhs metal layers like this. Where Foundry can't identify. This defective IC, if I send it to the market, means Qualcomm, I'm taking an example of Qualcomm just for example purpose. If Qualcomm has defective IC, if they give that to mobile phone manufacturer, if mobile phone manufacturer phone hangs in between, whether they'll purchase again from Qualcomm? No. So before forwarding the IC to the market, they have to test the IC. Right? Testing IC after fabrication is called as post silicon validation. Testing IC after fabrication is called as post silicon validation. Because see that is called as yield. Yield means what? How much IC you are throwing out for every 100 ICs, right? For every 100 ICs you are throwing 20 ICs outside, then yield is 80%. So minimum in a fabrication unit yield will be 60 to 70%. Means for every 100 ICs they will throw 30 ICs. 30 IC will be malfunctioning. Then how to test the IC? If I have designed the IC for Bluetooth controller, I cannot connect the antennas and I cannot check it immediately. So how to test the IC? So for testing the IC, right, the DFT team they are going to add some additional logic before physical design. This whatever the additional logics they are adding, right, that is going to help to test the ICs. Right? So DFT team will add additional logic to design without affecting functionality, so that chip, right? Chip means IC. Chip is easily tested after fabrication. Tested after fabrication. So the DFT team will add some additional gates in the design, gates, flip-flops. Right? They will add it. So testing IC after fabrication is called as what? Post silicon validation. Those DFT team, right? They will do scan chain insertion. So you will learn all these things. What is scan chain insertion and all. Scan chain insertion. They will do built-in self-test. Built-in self-test is a big twist, right? Twist. So they will do ATPG, automatic test pattern generation, ATPG, automatic test pattern generation. So they will do boundary scan. These are different techniques what the DFT team will use to make IC easily testable after what? Fabrication. After this, right, whatever netlist we get, that is forwarded to what? Physical design team. So our role starts here. Physical design. So now still the design is in what form? still the design is in what form? It is in the gate level form only, right? So even DFT team is going to add some additional cells. They have some logics to insert the cells. So based on that, they will add the cells without affecting what? Functionality. And after that, they will form the netlist to what? Physical design team. They will forward netlist only. Netlist is in what form? Gate level form. Gate and its connection. Now we have to convert into layout and its connection. That is what our role. Gate level design convert to the layout level. Gate level design convert to physical level. Physical level. Physical level means layout. What is physical level of a net? Here I told it, this is called as net, right? What is physical level of a net? This net. What is physical level of a net? Metal layer. Good. Physical level of a net is called as the metal layer. So gate level design convert to physical level design. That is what the role of physical design indicates. Okay. So we'll take a 10 minutes break till 11:10. 11:10 we'll take a break. So remaining thing what physical design is. So now you understood, right? Why physical design? The first question. So after synthesis, the design is in the gate form. You have to convert it to layout form. That is the role of physical design. So next we'll learn what we do in physical design. Next we'll learn what basics required for physical design. Then how the course works. That we'll see it in after the break. So 11:10 we'll start again. Take 10 minutes break. We'll start again at 11:10.
This conference will now be recorded.
Yes, sir. We'll continue again, right? So physical design. What we do in physical design? See, physical design we do lot of things, but I'll only mention the main steps. Because within the 3 hours, right, I can mention only the main steps. So what we do in physical design? So physical design starts with, right, mainly we cannot do physical design for entire chip if the chip is having physical design. I'll talk, right. We have two types again, right? Full chip design, and IP design. See, we physical design again have two types: full chip design and IP design. See, many engineers will not work in full chip design because it's a layer condition, but many companies will work on IP design. IP design is nothing but directly. So I'll give you one simple example, right? What we purchase in shop, puliyogra mix, right? Whatever the mix we have, puliyogra mix or any other masala mix, right? That is called as IP design. We don't cook from the basic level. We don't do all these things for some. If, for example, there are few circuits like processor, RISC-core processor, right? Like some PCI controller module or like Ethernet module, right? Ethernet module. Like we have I2C communication module. For all these things, they'll create IC and they'll keep it. Many companies will work only on IP design. They not work on full chip level design. And they will tell that our IP is best, right? All the companies will work in designing IPs with the what optimized way. Means it should be consuming less area, less power, and good in timing, right? So after that, they will sell the IC. This ICs, they'll sell the IP. IP means intellectual property. They'll sell the IPs. These IPs are taken by full chip level designers, and full chip level designers will integrate these IPs. Right? Full chip level designers, they will not worry. The full chip level designer, for example, he want to implement a processor. He want to implement a processor means what he will do? He want one ALU. You purchase ALU IP, right? Purchase ALU IP, arithmetic logic unit IP you purchase. Just I am telling in basic terms. ALU IP and controller. So we have to control all the arithmetic and logic units, right? Controller IP you purchase. Memory IP you purchase. You want memory, right? Memory IP you purchase. And you integrate all these IPs. Integrate means what? Connect all the IPs. This is called as full chip level design. So full chip level design is nothing but integration of block level design or IP design. So this is called as IP or blocks. IP, or it's also called as what? Blocks. This intellectual property or blocks. Right? So this process is called as even partitioning. If I have full chip, right? If I have full chip, if I have more cells, what they will do? They will partition into what? Different blocks. This is B1 block. This is B2 block. This is B3 block. And each and every block is given to one engineer. They will do physical design for each and every block. And these blocks are given to the full chip level designer. He will integrate all the blocks. And after integration, he will generate GDS2 file, and that is sent to fabrication. See, full chip level engineer, he will split this entire design into different blocks. So that is called as partitioning. Or full chip level design engineer, he can directly purchase the blocks from the already available IP owners. Like you have a company called as Samsung. They are not in the manufacturing. They are only generating IPs. There are many companies which are generating only IPs. Only they will fabricate, they will design IPs. IP means intellectual property. This is a physical design. All these are physical, means all these are layout information. Just give layout information to the full chip level design engineer, they will integrate this. So now how this IP design works? What is full chip level design? Full chip level design is nothing but integration of block level design or IP design and block level design both are same. The full chip level design is integration of all blocks. Because physical design cannot be done for cells which is having 10,000 cells, that is 10,000 of 10 lakhs gates. Right? We can do physical design max to max 1 lakh gate. So for that reason, first we will build small blocks, and that blocks are integrated to form what? Full chip. So this is called as full chip level physical design. So this involves integration of blocks and IP design or block level design, right? This has all these steps. It has floor planning. The physical design has all these steps. So we are going to do a physical design of a block level design or IP design. So physical design of block level design, IP design has these steps, right? Floor planning, placement, CTS, is clock tree synthesis, derouting, right? And in each stage we have to do STA. STA means static timing analysis. Each stage. In each stage, placement do STA. After CTS do STA. After routing, you do STA. Each stage you have to do STA, static timing analysis. So floor planning. What is floor planning? For your block, right? For your block or for your IP, whatever you're designing, first you have to estimate area and create core area and die area. Create core area and die area. From the netlist, you will be knowing for your block or for your IP how much area is required. For cells, right? For each and every cell in the netlist, right? The area information is also present in Liberty file. We have timing, power, right? Even we have area information also. How much area the each and every cell will take. Area means what? This area of a layout, right? Area of a layout, how much area it will take. That information is present in Liberty file. From that, I can calculate how much area is required for entire design. From that, I can create core area and die area. What is core area and die area means? First step is creating core area and die area. So this is your core area and this is your die area. I have to create in this area only. I have to design my entire block. So this is inside block is called as core area. So inside this core area only we are going to place all the standard cells and macros. So outer region is called as die area. We have to create core area and die area. So after this, right, we have to after this step, next step is port placement. After that we have macro placement. Next we have power planning. These are the major steps in the power planning. Port placement means place the ports, right? Here place the ports. Ports are nothing but inputs and outputs of a here, right? What are the ports here? In this netlist, your ABC is what input ports and Y is a output ports for this block or for this design, right? So place those ports. So here, this is a logical description. Physically, these ports will convert into what metal layers, right? So ports are nothing but metal layers. ABC ports you place here, Y port you place here. Place the ports like this. Ports are just a metal layer. They are just metal layer. This port is like some A port, right? B port, C port, and Y port. All the inputs will come through these ports, and output will go through these ports. In your design, I need not to have only one port, one output port. I can have many output ports. Plenty of output ports I will be having in a design. I can be having many output ports. Called as port placement. Port placement means this logical description, input and outputs, right? Whatever we have for the block that you place in the form of metal layers. That is called as ports. So we have plenty of rules to place the ports that we will study in the course. How to do the port placement. Next is macro placement. What are macros? See, ports are input and outputs of a block. Input and outputs of a block. It's called as port. But we are going to do the port placement. Next is macro placement. What are macros? See, in this IP design, again I can use some other IP. In this IP design, is not only it is an interconnection of standard cells. In this IP design, I can use some other IP also. For example, macro means macros are complex cells. Complex cells which are already optimized. Already optimized. Optimized means they are the best cells for that functionality. For that functionality, they are the best cells which are already optimized. Those are called as macros. See, for this macros, right? See, in that, for example, in my design, I want ALU block. You assume, right? I want arithmetic logic unit block. If this arithmetic logic unit block, or I want memory block, you assume I want memory block. I want 10 memory blocks. SRAM I want. SRAM 10 memory blocks I want. I am implementing a processor or microcontroller. In this microcontroller chip I am forming. For this microcontroller chip I want 10 memory blocks. Whether you expect me to write the Verilog code for 10 memory blocks, write the Verilog code, do synthesis for 10 memory blocks and implement as a physical design. For example, each memory block is having 10,000 cells. Each memory block is having 10,000 cells. How many extra cells I will be having in the netlist? For 10 memory blocks. For 10 memory blocks, I will be having how many extra cells? I will be having almost 1 lakh extra cells, right? If this 10 memory blocks, if I go through the process of Verilog coding, doing synthesis and doing physical design, if I do, in my design, I will be having 10,000 extra cells. Not 10,000, right? 1 lakh extra cells. Instead of that, I will directly purchase the layout. I'll directly purchase the layout of these memories, right? Layout of the memory blocks. I'll directly purchase layout of a memory block from IP vendor. Even whatever block level design I am doing, right? This is also I can sell it as a IP to some other person. He can use my block. Okay? See, you are doing cooking you are doing. So you are the block level designer. You're doing the cooking. You cannot do everything from the basic level. Directly you will purchase puliagra powder and directly you will purchase rasam powder from the shop. For your design, they are the IP vendors. Directly purchasing there. Directly you are purchasing puliagra powder. Whatever cooking you are making, right? That again you will supply for some other person. He will use your cooking, whatever you have done, and he will add his additional things, and he will make his own dining party hall or dining party room by taking your cooking. So similarly, your design is a IP for some other's design, and even your design you may use what some other IP. So 10,000, so 10 macros I can directly place here. I am directly placing layout of a macros. What are this? Layout of a macro. So directly I am placing it. I am not going to do physical design for this memory elements. Because for each memory element, if I start doing physical design, right, each memory element will give me 10,000 cells. Totally, I will be having 10,000, 1 lakh memory elements only. Means this is having small cells, right? Small NAND gates, AND gates, everything. This is having small things. If I don't purchase this macros from a vendor, then I have to do it, physical design. I have to write the Verilog code for this. That is very difficult. For that reason, what we do is in every design we will be having few things called as macros. Right? These are all macros. Macros are complex cells which are already optimized. We directly purchase from a vendor and we use it in our design. So we use memory macros. So these are all layout of a cell. So this is layout. Layout in LEF format or frame view. It's a layout. All the layout will place. In a design, macros will be of small count. Like it will be like if you have 50,000 gates, macros will be like 40 or 20 count. So for that reason, first we will do macro placement. So macros are complex cells which are already optimized and directly will place layout of those cells. See, along with these macros, we will be also having some analog macros. What are analog circuits? Analog circuits are the circuits which cannot be fabricated through this process, ASIC design flow process. ASIC design flow works only for the digital design, not for the analog design. Digital design means these circuits will work only with logic 0 and logic 1. There are some circuits called as analog circuits like amplifiers, analog circuit, op-amp, analog circuit, comparator, analog circuit, phase lock loop, analog circuit. So in your design, if you want phase lock loop, you cannot write the Verilog code for that. That analog design engineers, they will design, analog design engineers, they will design and they will draw the layout. That layout you directly use in your design. This is analog macro. Even I can use analog macros. No, we can get separate library files for macros. See, macro vendor will give the files. Standard cell library designer is different. The standard cell library designer is different. Macro designer is different. So I will get separate library file, separate .lib and separate LEF for macros. For macros, I will get separate .lib and separate LEF. For analog macros, I will get separate .lib and separate LEF. Macros are nothing but these are all the small circuit which will go through all these steps only for this macros, right? No. They can be different library file. Library file need not to be one library file. You can have n number of library files. Separate library file for standard cells. Separate library files for macros. Separate library files for analog macros. You can be having separate library files in design. Library files not to be your question is whether we have to use only one library file. So no, not like that. You can be having n number of library files and different for different cells. I can just tell to the tool, look into these library files when you're working. That's it. We have options for that. So what are macros? I repeat once again. Macros are the complex cells which I don't want to do the design of this macros from the beginning. I don't want to include in this designing part. I don't want to write the Verilog code. See, macros are instantiated during RTL design only. For example, your RTL requires 10 SRAM blocks. You have to write the Verilog code for 10 SRAM blocks. Instead of that, directly use the macro name. For example, that macro name is SRAM. Directly use that macro name and instantiate what is the input for those macros. What are the inputs for those macros? What are the inputs you are passing, right? You instantiate in RTL only. We are describing the macros in RTL only if you use in the design. What is the advantage of using macros is we are not going to write the logic for macros in RTL. We are not going to write any logic, sir. What is present inside a macro. During synthesis also, we are not worried what is present inside macro because for macros, we directly have .lib. For macros, we'll directly get the .lib. This .lib. Directly we'll get .lib and directly we'll get the layout. Layout in the form of what? LEF file. That layout will directly place here. The advantage of using macros is cell count will reduce, right? For example, each macro requires 10,000 standard cells to implement. I am not implementing it. Some other person is already implemented. He is directly giving me the LEF file after implementing. My Foundry wants what? Only layout information. My layout information I've already taken from some other person. Why I want to implement it once again? Right? Ultimately, Foundry wants layout. Layout I already purchased it. If you don't want to purchase, then you write the Verilog code to do synthesis, to do everything. If you have a habit of purchasing, you purchase it. That is what all the companies will do. None of the companies will do their IP product based companies, right? Like Synopsys, Intel, they will not do in their own company, especially physical design. They'll outsource everything. IP design, they'll outsource. Means this each and every IP, right? They'll outsource to the service based companies. So service based companies will do the physical design of the small blocks. See, we are not worried about functionality of a macros, physical design engineers, because we want layout. Functionality is required by gate level simulation team. Gate level simulation team requires what is the functionality of a macro. They will give some specific functional models to the gate level simulation team. They will give some functional models for that. But physical design engineers requires only layout of a macro, and my chip architecture has told that use this layout. We don't have any problem. They should ensure that this macro is working fine. It's working good with the timing. It is implementing required functionality. Then I can directly use this LEF and I can place in my design. So the advantage is I need not to design this macro from the beginning. I'm directly using in my design. I gave you an example, right? If I'm doing the cooking today, I need not to do the puliyogara mix from the beginning. I will directly purchase from the shop and I'll mix with my rice. Directly purchase the macro from the vendor and mix with your design. That's it. Effort of designing a macro is reduced. That is called as macros. These are called as hard macros because I have only layout information. Even you can directly purchase RTL also as a macro. That is called a soft macro. You know what is the functionality inside a macro. You know that. That is called a soft macro. That you'll understand later in depth, right? So next step is this macro placement. So macros are complex cells which are already optimized. So if you want to use any complex cells in your design which are already optimized, then you can use it and you can place it. It's not necessary that in all the blocks or all the designs should have macros. If you feel by purchasing a macro, my timing efforts will be reduced, then do it. Timing effort means runtime will be reduced. So I can go to the market very fast. Then directly purchase the macros and integrate it. So puliyogara mix also you'll purchase for the same reason, right? Because your cooking should complete very fast. For then only you'll purchase it. Same the macros also. So after macro placement, you have to do power planning. So in power planning, mainly done to reduce IR drop. In power planning, I have to plan how to distribute the power to entire design. See, every cell should get every cell has VDD and VSS connection. You see the layout, right? Every cell has what VDD and VSS connection. In my IP design, I will be having nearly 1 lakh cells. Yes, they can be placed in same substrate, but you should take some extra precaution for analog macros, right? You can take some extra precaution for analog macros, like you can use some guard band, because analog macros can create more noise to the digital macros or digital circuits. They can create more noise because they are changing continuously. But for my digital macros, they are changing only at particular time, means logic 0 or logic 1. But analog macros, they will be changing continuously with respect to time, like this. They can create noise for digital circuits. If the, see, for example, I have any one circuit nearby to this, right? Any one circuit I have near to this analog macro. If this signal is changing continuously, like this, inside this, my digital signal, logic 0, logic 1, it will be having spikes like this. So this is called as noise introduced by analog macros. To avoid that, I can be having some guard band. Means in this region, no, don't place any cells. I can use that. Analog macros, I can use some guard band. So power planning mainly done to reduce what? IR drop. So why IR drop? So power planning, right? We plan in power planning, plan to distribute power for entire block. How to distribute power for entire block? See what happens. What is IR drop? Is, for example, I have one cell here. Assume I have one standard cell. This standard cell is having VDD connection. I am taking VDD connection from somewhere here. I'm having VDD connection from somewhere here. This is a metal layer. What is this? Metal layer. Right? Here, VDD, you assume it is 1.5 volts. And when the cell is switching, it is going to draw the current. It's going to draw the current. As it's a metal layer, right? Metal layer has a resistance, small resistance. And current is also flowing through metal layer. So because of this, what happens is the voltage drop happens on the metal layer. That is called as V is equal to I into R. It depends on how much current a cell is drawing and what is the resistance of this metal layer. Some voltage drop is going to happen on these metal layers. Out of 1.5 volts, 0.2 volts will drop on metal layer. Then how much volts will reach to the cell? 1.3 volts. This is called as voltage drop. VDD is going to drop. If this VDD drop happens, by using dot lib, I assume this cell is having in the dot lib for 1.5 volts, the cell delay is like 0.5 nanosecond. But how much voltage is dropping in reality? How much voltage it is reaching to the cell? 1.3 volts. So I assume, see, I have done the design by assuming that the cell delay is 0.5 nanosecond. But in reality, right, for 1.3 volts, the cell delay will be 0.75 nanosecond. It is more than what I have estimated because of voltage drop. This voltage drop happens because of this metal resistance. Whatever intended VDD, whatever we have, that will not reach to the cell. So if that intended VDD is not reaching to the cell delay increases. I have closed my design by considering the cell delay as what? 0.5 nanosecond. But in reality, the cell delay is 0.75 nanosecond because of voltage drop. This is very dangerous. That we have to reduce. To reduce that, we have to do power planning. Right? So that we will study in physical design. What power planning we do. See, we'll create rings, we'll create stripes, we will create rails, all those things we will study. How to do power planning to have less IR drop or minimum to minimize IR drop. After that, placement, right? Placement step, right? Place all standard cells. Till now, we have placed only macros. Macros are complex designs, and even their count will be very less. If I have 72,000 standard cells, macros will be hardly 30 to 40. So only I have placed macros. Now place standard cells. Place all standard cells inside core area. I have to place all the standard cells inside core area. Place it. Okay. So how to place all the standard cells inside core area? My tool will place it. I am not going to place it. Right? my tool is going to place all the standard cells inside core area. So now we are started placing all the standard cells. So what are the standard cells? These are layout of standard cells. Here I use LEF file. What I am placing here? Layout of standard cells. We are not going to draw the layout. Layout team is already drawn the layout and they are given in the form of what? LEF file. So just we are placing in the core area. Layout of the cells. See, this placement is not simple or straightforward. Placement has lot of rules we have to follow to do the placement. See, placement I have to do in such a way that, right, all these constraints are met. Sorry, not this one, right? This placement, I should see that my design is consuming less power. I should do in such a way that my design is meeting the timing. What is the timing requirement? Means timing requirement means my design should operate with the required speed, required clock frequency. Now place the standard cells inside core area. So after placement, we do lot of checks like we do congestion checks, we do congestion. Congestion means whether I have sufficient space for routing cells. I should route the cells, right? Routing is not at done. Routing means connecting the cells according to the netlist. According to the netlist, right? This connection. Output of Y1 is connecting to what? Input of A1. This called as connection, routing. So whether I should be having sufficient space for routing, right? That is called as congestion check. Whether I have sufficient space for routing. So we do timing DRV. We do static timing analysis STA. All these checks we do, and we do even power power check, power connectivity check. Means all the standard cells are getting VDD and VSS power or not. Right? Power connectivity check. All these checks we will do after placement. After that, see, you will understand what is this check, right, in that course. I cannot cover in the 3 hours class. To understand, just I can mention whatever we are doing. STA to STA only we require 1 week. 1 week we require to do only explain what is STA, static timing analysis. Minimum 1 week we want. Next is CTS. What is CTS? Clock tree synthesis. Why we have to build a clock tree? See, I have a design, right? I have a design. I have many flip-flops. All the flip-flops needs a clock. So in a design, I will be having thousands of flip-flops. And these flip-flops will get a clock only from a clock port. You will be having a clock port. From this clock port, all these flip-flops will get connected. I guess they get connected. See, on the clock port, right, the load will be very huge. I'm having very huge load. Why? Because see, this clock port is having a capacitance, a load capacitance. This load capacitance is nothing but net capacitance plus pin capacitance. What is net capacitance? Net capacitance means the capacitance of this metal layers. The capacitance of this metal layers is called as what? Net capacitance. Pin capacitance means the capacitance present at pin of each and every cell. That is called as pin capacitance. Every cell is having pin capacitance because you see the gate of a cell, right? If you see the gate of a cell, this gate, top you have what? Polysilicon connected to positive voltage. Here in the channel you have what? Electrons. In between you have silicon dioxide. It's going to form a parallel plate capacitor. So this capacitance is called as pin capacitance. Each and every flip-flop has, or each and every cell has pin capacitance at the input. Right? If this pin capacitance is like 1 Fermi farad, 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 then what is the total load capacitance? If I have 1000 flip-flops, it's 1000 Fermi farad. 1000 flip-flops I have means here I have 1000 Fermi farads of load. Only pin capacitance. Along with that, I have net capacitance. Net capacitance is like 500 Fermi farad. Totally 1500 Fermi farad of load capacitance I have here. So, if my clock is rising, clock is falling, clock is rising, clock is falling, means I have to charge this load capacitance, I have to discharge this load capacitance. Clock is rising means charge the load capacitance, clock is falling means discharge the load capacitance. This much huge load capacitance for charging, right? I will take more time to charge. Changing is not instantaneous. Changing will take the time based on the load capacitance value. This load capacitance value. If this is a huge load capacitance, then I'll take time to charge. I take time to discharge. My square waveform has now become what waveform? Triangular waveform. Because of more transition time, rise time and fall time. Because of huge load on the clock pin. If I directly connect all the flip-flops to the clock pin, right, I'll be having huge load on the clock pin. So to reduce that, what we do is we'll build a clock tree. This capacitance, I'm not connecting it. This capacitance is formed because of the nature of metal layers and nature of pin capacitance. They are formed. So because of that, what we do is we will build a clock tree. What is clock tree? Well, for example, I want to connect these cells, means first this port I will connect to only 2 buffers. Now what is the load on this port? Pin capacitance of this, pin capacitance of this. So what is the load here? Just 2 Fermi farad. 1 Fermi farad here, 1 Fermi farad here. How much load? 2 Fermi farad. Then this rise time will reduce, right? Because now I can easily charge my load capacitance and I can easily discharge it because this value is very less. So I can easily charge means I'll easily charge like this and I'll easily discharge like this. Now this buffer I'll connect to this flip-flop. This buffer I'll connect to this flip-flop. But this flip-flop is very far. If I connect directly, right, the net capacitance will increase. The load will increase on this buffer now because of this long net. Long net has more net capacitance. So here load will increase. So decrease the load, what I do is again I will use one buffer here. So the now load is less, right? Because less net capacitance. So this buffer is saying only pin capacitance of 2 cells, only small net capacitance because of shorter net. Again, this flip-flop is very far. Use one more buffer and connect these 2 flip-flops. Again, use one more buffer. Connect this flip-flop. Use one more buffer. This flip-flop. Now each buffer, if you see, this buffer is saying only pin capacitance of this buffer and this net capacitance. This buffer is saying only pin capacitance of what? This flip-flop, and this buffer, and only small net capacitance. Net capacitance depends on net length. So to reduce the net length and to reduce the fan out means what? One cell is driving how many cells? So fan out of this cell means this buffer is driving only one flip-flop. Here fan out is 1. For this buffer, what is a fan out? 1, 2. 2 is a fan out because it's driving this cell and this flip-flop. For this buffer, what is a fan out? 1 because it's driving only one buffer. This buffer, what is a fan out? 1, this one and this one. 3 is a fan out. For this buffer, 1 and this one, this buffer 2 is a fan out. For this buffer, 1 is a fan out. To reduce fan out and to reduce the net length, right, we build a clock tree like this by inserting buffers. We build a clock tree by inserting what? Buffers. So See what happens is here the clock edge, whatever I am seeing here, this clock edge, whatever I am seeing here, this clock edge, I will not see this clock edge is 0 nanosecond means to this flip flop I will get this clock edge after 1 nanosecond delay because I have delay of buffer here right now. This clock edge will reach to this flip flop after 1 nanosecond. The same clock edge may reach to this flip flop after 3 nanoseconds because I have in between I have how many buffers? 1, 2, 3, 4 buffers. This edge will reach later, but the clocks will be having some shape, right? The shape will be there as it is. This shape is maintained. The clock shape is maintained like this. Clock shape is maintained. I have not lost the shape. Rise time and fall time is less. This rise time and fall time is what? Less. The clock shape is maintained. But this clock edges, right? It will reach late to the flip flops. Here, this clock edge is coming at 0 nanosecond at this port. But this clock edge will reach to this flip flop after 1 nanosecond. To this flip flop, it will reach 1, 2, 3, 4 after 4 nanosecond. To this flip flop, it will reach 1, 2, 3, 4, 5 after 5 nanosecond. It will reach later, but the shape is maintained. The clock shape is maintained. I have less rise time and less fall time. If I have more rise time and more fall time, what happens? Instead of triangular wave, I'll start getting, instead of square wave, I'll start getting triangular wave. Right? To reduce the load on the clock port, to reduce the fan out, to reduce the net length, we build what? We build clock tree. See here, edge I am getting at 0 nanosecond, but for this clock I am getting after 1 nanosecond, right? Because I have buffer delay. This is called as latency. Latency is nothing but time taken by a clock edge to reach to the flip flops. For this flip flop, latency is 1 because after 1 nanosecond the clock edge is reaching. For this flip flop, the latency is 1, 2, 3, 4, 4 nanosecond. Time taken by a clock to reach to the flip flops clock edge is called as latency. So because of this insertion delay means whatever buffer we have inserted, that is called as insertion delay. The clock edges may reach later to the flip flops, but the shape is maintained. The clock shape is maintained. That is why we build a clock tree to maintain this clock shape. Or else instead of square wave, I will be getting triangular wave. That is what is clock tree synthesis. Build a clock tree using what? Using buffers and inverters. So we do all these checks again. After CTS, we do all these checks again. Whether power is reaching to all the cells, because additional cells are inserted right now. So in this design, along with the standard cells, now what are inserted? Buffers are inserted here and there. These buffers will come into picture, new buffers. Inside macros, we are not worrying. We will not touch anything inside macro. Only whatever we do, it is external to macro. Inside macro, I already told you, it is called IP because of what? The macro is the best macro. That is why only we will purchase. Everything they will take care inside. So we have to think only till macros. Even macros also will be having clock pin. So we will worry only till reaching to macros, not inside macro. So along with this checks, right? After CTS, we also check what is latency. Latency means what? Time taken by a clock signal to reach to the flip flops, right? Maximum latency. So what is the efficiency of my CTS tool? A CTS tool should build this clock tree with less latency, right? Less latency or less insertion delay. Less insertion delay means less less amount of buffer should be inserted. That is the efficiency of my CTS tool. So less latency means the clock which is reaching here at 0 nanosecond, it should reach the flip-flops very early. It should not take more time to reach. We also check what is latency, what is skew. So here in STA, before CTS, we do only setup analysis. Here we do only setup analysis. After CTS in STA, we do setup analysis as well as hold analysis. Both will do. Setup analysis and hold analysis, both will do. Q means a difference in time reaching the flip-flops. See, for first flip-flop, the clock is reaching after 1 nanosecond. For this flip-flop, clock is reaching after 4 nanosecond. What is the difference in time? 4 minus 1, it is 3 nanosecond. That is called as Q. So difference in time, clock reaching to the two flip-flops. That is called as Q. Check. So my CTS tool should build the clock tree with less Q and less latency. So last step is routing. Routing means connect all cells using metal layers. I should connect all the cells by using metal layers. These cells. And all the cells by using metal layers. These cells we connect by using metal layers. According to the functional requirement, connect through metal layers. Without shorts. I should not shorts. Standard cells, macros, ports, everything we have to connect to metal layers. That is called as what? Routing. Connect all cells, macros, using metal layers. After routing, we have to do what? All these cells are layout of a cells and macros are layout of a macros. So macros will get in a file called as LEF file. That file we'll use and we'll place a layout of a cells here. Here it is a layout of a cells. Here we are connecting layout of a cells. Layout we are not drawing it. It is drawn by layout team that we are using it. Connect all cells, macros and ports using metal layers. So after this, what checks we'll do routing? Mainly we do DRC check. DRC and we do LVS check. DRC stands for what? Design rule check. LVS stands for layout versus schematic. Design rule check means the Foundry has a rule between one metal layer to another metal layer. You should be having minimum spacing. You have to maintain minimum spacing. So minimum width of a metal layer, this should be this much. You should not use width lesser than this. So Foundry has a rules. That rules is given in a file called as TF file, technology file. So my design should meet this rules given from Foundry. Foundry has plenty of rules. So we have to do routing, placement, building CTS by following these rules given from Foundry. If we don't follow, what happens? My Foundry cannot fabricate. That is called as design for manufacturability. So I have to follow all the rules and regulations given from the Foundry, compulsory. My Foundry tells within this region you have to maintain minimum percentage of metal layers. In this region, in every small regions, minimum metal layer percentage of metal layer should be 30%, maximum should be 70%. Then only I can fabricate. Then I should see that in particular regions, in every small regions, 30% and 70% I should be having metal layers. Minimum I have to maintain 30% metal layer. Maximum I should maintain 70%, because if I maintain less than 30%, right? I told you during etching process I will treat with acid. That high concentrated acid will also remove the 30%. To treat with acid, I should be having minimum metal density. So all those rules are present in TF file. That rules I have to maintain. Whether that rule is maintained or not is verified by what? Design rule check. Layout versus schematic. Layout versus schematic means here we don't have schematic. Here schematic is nothing but our netlist only. This netlist. This netlist only is schematic. Whatever connections mentioned in this netlist, the same connection should be present in what? Layout. We should not miss it, because it's not like one connections or two connections. We have thousands of connections or lakhs of connections. What are the connections present in the netlist? The same connection should be present in layout. This layout. For example, this connection was present in the netlist. It is missed in the layout. This connection is missed. Then this pin is open. This pin is open. These two pins are open. For example, there is no connection between output of this cell and this pin, but I want to route from here to somewhere here. I want to route. While routing, I have shorted in between here, right? I have shorted here. The meaning in the layout, what it is showing, the output of this pin is connected to input of this pin. But this connection is not present in the netlist. Right? This is called a short. So what connections are present in the netlist, right? The same connection should be present in the layout also. Layout means this physical design. That is called as layout versus schematic. That check we will do. So layout versus schematic can report in shorts and opens. Shorts and open. Shorts means unnecessary connections happen. Opens means which is not connected. That we have to do. So next STA. STA is not only done here, right? Here also STA is done. Here also STA is done. After routing also we will do STA, static timing analysis. STA is done every time. So what I want to tell is, along with all these things, all the steps of physical design, we also cover STA, static timing analysis. In STA, we will cover what is clock skew, right? What is latency, what is clock latency, what is transition. So we will cover setup time, setup and hold analysis. So we will cover PVT conditions, process voltage temperature, how this process voltage temperature affects cell delay. How is process voltage and temperature affect cell delay? That we will cover. And we will cover multi-cycle path, false path. What is false path? Half cycle path. Asynchronous circuits. How to handle asynchronous circuits. So we will cover all these things in STA separately. STA is done before placement. Before starting placement, we'll do STA. After that, we'll do sign off checks. Right? Sign off checks are mainly are three types. Right? First is IR drop, and power check. Means how much power your tool is consuming. Right? Your design is consuming how much power, and how much IR drop is happening in your design. That check we'll do. That is done by using a tool called as RADAC, a separate tool. RADAC tool. It's not done in, see, for physical design we use ICC2. For physical design, we use what? ICC 2, integrated circuit compiler 2. But for RADAC, right, for sign off checks, IR drop and power check. See, based on this IR drop feedback only, we will do this power planning. They will be having experience for this type of circuit to do power planning. From their feedback only, we should do power planning. After doing all these things, my IR drop team will check how much IR drop is happening. So my team will tell like this. So in this region, there is more IR drop. Reduce it. So then I have to reduce IR drop. I have to insert like some decap cells. I have to change my power planning. I have to reduce IR drop. After routing, my role is not completed. I have to take care about all these checks. If they give any feedback, I should be implementing that. So after that, we have timing sign off. Timing sign off. In timing sign off, mainly we do STA. Here also we have done STA. At the last also we will do STA. To do STA here we use prime time tool, separate tool. In ICC2 also we can do STA, but we do separate tool here because this is accurate compared to ICC2. Prime time is accurate compared to ICC2. Here we use prime time. So we will do static timing analysis by using prime time. And third thing is physical verification. STC, right? Yes. Here, right? STC. PVT conditions and STC. Here STC is not straightforward. Here it is STC we have to write for different modes, different corners and different scenarios. We write the STC that will cover. So last timing sign off is physical verification. Physical verification is done in IC validator. In IC validator, separate tool. Physical verification will check same thing, right? DRC, LVS, ERC, electrical rule check. DRC, LVS, electrical rule check, ERC. So all these checks it will do. So when your block meeting all these things, right? When you block your IP, you are meeting all, then you can send this to what? Full chip level designer. Full chip level designer will integrate all the blocks like this. He will integrate all the blocks. After integrating, he will generate what? GDS file. Then he will forward this to Foundry. So in this block level design, what we have? We have layout of a cells, right? And we are doing layout connections. See, our role is not only to place the cells and do connections. We should always also meet what I told you, right? We should meet timing. We should do power effective design. Unnecessary, we should not use a not waste power effective design. Next is, right? Functionality should not be disturbed. I should not disturb the functionality. After doing all these things, and if you do logic equivalence check, logic equivalence check means extract netlist of this layout. For this layout, you extract the netlist. This netlist you compare with RTL. Both should implement same functionality. If functionality is not met, gone. That's it. So functional equivalent design we have to create. You should not disturb functionality. Means I should not interchange the connections. Cell connections I should not interchange. I should be very careful about that. So we have to build functional equivalent cells, and we have to meet design for manufacturability. Design for manufacturability means so my design should be fabricated. Means I have to follow what are all the rules given from the foundry. If I don't follow, my design cannot be fabricated. So all these things we have to take care while doing physical design. Most of the designs are IP or block level physical design. Only few percent of design will be full chip level design. Because full chip level, most of the time it uses what? IPs or block level, and this they will integrate it. While integration, they will treat my block as macro. That's it. Right? What I have done here, while creating block level, I have treated some other design as macro, right? While integration, my full chip level design, he will take this block, he will use in his design, and he will consider my design as what? Macro. And he will do the physical design. That is called as full chip level design. But full chip level design, slightly it varies. Here we have placed ports. Right? Here we have placed what? Ports. Here we place IO cards. Because these IO cards, my ports will interact within a chip, but IO cards will interact with outside the chip to inside the chip. It will take outside signals, right? From outside signals, the signal will first come to IO cards and it will go into inside the chip. So full chip level designers is going to place IO cards in between core area and die area. But in the block level design, we place what? Ports. Ports are simple metal layers, but IO cards are not simple metal layers. Inside IO cards, we have level shifters, means voltage shifters. If outside voltage is different and inside IP voltage is different, then I should be using level shifters. ESD protection cells, electrostatic discharge protection cells. So all these cells will be present inside a IO card. It's not just a metal layer. So these are some small difference between your full chip level design and block level design. No, it's not required. Taking out different layers of metal. That I'll discuss in the full this full advanced courses. Now, what is the basics required? Yes. No, we are not going to do full chip level design. We are going to do only block level design. We will do only port placement, not IO placement. See, generally full chip level design is required who wants to claim 5 to 6 years of experience. So they only can work on full chip level design. Full chip level design is nothing but partition the logic integrated. So to that level of experience, you want full chip level information. But generally, when you go with the 2 years of 3 years of experience in physical design, you should be knowing thorough block level implementation. And full chip level design, it is hardly 20% of it, but 80% of engineers work on block level design because block has to be implemented individually. That will be integrated to the full chip. So every company will outsource it, all the block level designs. So that reason only we have many service based companies. Service based companies mainly they work on block level designs, and if there is a ODC project, even they work on full chip level also. ODC means entire project is outsourced. Entire chip design is outsourced. So basics, required basics. No doubt you want digital design. right? So no doubt you should be knowing what is mux, what is B flip-flop, what is asynchronous circuit, what is synchronous circuit, what is latch, right? Because even this information we want to do STA, static timing analysis, how flip-flops works, right? That information should be good, known, that is required in digital design. What is asynchronous circuit? What is synchronous circuit? What do you mean by asynchronous reset? Like that, you should be knowing some terms to do physical design. And you want TCL tool command language, you should be knowing Unix because normal EDA tools will use Unix operating system to work. The one of the advantage of Unix operating system is Unix has built-in commands that is very helpful to do the work very easy. Unix is required. You should be knowing Unix, what is grep command, what is awk command, because we'll do many file operations in the design, right? In the physical design, we will do many file operations. Like, for example, if I dump any timing reports, STA timing reports, if I dump, right, to extract any information from the timing reports, I should be knowing what is grep command. I should be knowing any awk command to get any one column. I should be knowing awk command. So Unix is very important. TCL is also very important because EDA tools will understand only TCL. EDA tool means electronic design automation tool, which we use to design the circuits. For physical design, we use ICC2 as EDA tool. So many EDA tools will understand only TCL. Even your Xilinx also will understand only TCL. Apart from user interface, if you want to talk with the tool or communicate with the tool, you can do only through TCL. EDA tools understand only TCL. So you should be knowing strong knowledge of TCL, how to use TCL, what is basic commands like set, puts command, set command, what is loop, what are different loops you have in TCL, for loop, while loop, for each loop, how to do file operations by using TCL, what is list commands, right? TCL support list operations, what are list operations, what are arrays in TCL, what is string operations in TCL, what is regular expression in TCL, we should be knowing all these things. Next, you should be knowing about CMOS fundamentals. CMOS fundamentals means what is MOSFET? What is the operation of MOSFET? What is structure of MOSFET? Structure of MOSFET means a MOSFET has this P substrate N well, right? PMOS is fabricated only in N well, right? Like that. Structure of MOSFET. And CMOS circuits. How to implement NAND gate by using CMOS circuit, NOR gate by using CMOS circuit, CMOS circuits, and layout. How to draw the layout for NAND gate, NOR gate. Anyhow, we are not going to draw the layout, but having the knowledge of layout is important. Layout information. So we have CMOS fundamentals for that. These are the basic things required to start with advanced physical design. So for this reason, right, our course, entire physical design course is split into two things, right? Physical design course. Split two things. One is advanced part, advanced PD. First is basics PD, plus advanced PD. So basics PD generally it will take place for 2 months, and advanced PD is for 3 to 3.5 months. After 2 months, you will be having basics PD. In basics PD, all these topics are covered. In advanced PD, It is for 3 to 3.5 months. Here advanced topics of physical designs are covered. So each and every step, floor plan 20 days, placement 20 days, CTS 20 days, like that. So we'll do advanced part in advanced PD. So basics is for 2 months and advanced PD is for 3 to 3.5 months. So it's overall 5 to 6 months course, including basics. Right? First basics. We'll start with basics first. Basics PD. It is only on weekdays. Weekdays from Monday to Saturday. Basics PD. Advanced PD. Advanced PD. We have from Monday to Friday. Right? So we have advanced PD works with weekdays and weekends. Right? Weekdays. Weekdays is from Monday to Friday. Right? So this is only lab, weekdays lab we have. Weekdays lab you will work on tool here. Advanced PD you are working on ICC2 tool, and we have weekend lab. Weekend lab also available because for the working professionals who are not available in weekdays. For them we have weekend lab that is only on Saturday and Sunday. This advanced PD only about lab. So theory, right? Advanced PD theory is done only on Saturday and Sunday. So we'll do Saturday and Sunday theory. So from Monday to Friday, you will be working on lab. And for working professionals, if they are not available on weekdays, they will work on labs on Saturday and Sunday after theory classes. Morning you will be having theory, afternoon you will be having labs Saturday and Sunday. But basics is from on weekdays, from Monday to Friday. There is no separate course like weekend or weekdays. That if you are not available, please talk to the admin. So they will provide you the alternate things they will suggest you what you should do. And here, one more thing I want to suggest is so institute will give you, yes, anyhow that is only on, see that you can talk to the admin. That is both are available. Theory is only on weekends. Lab is available. Both labs are different. Weekdays labs are different. Weekend labs are different. The students who are not available on weekdays, they can only opt for weekend labs. Is about the course. So this basics is for only weekdays. Basics. In basics, it is covered. See, if you are not available on weekdays, right, please talk to the admin. Right? We will give you the alternate options. If you are in the group, you can message in. So they will give you alternate options what you can do. And videos will be given. Right? Recorded videos are given. Live recorded videos means it is not recorded videos of any other batch. The current batch recorded videos are given. After, for example, today class completes, within 6 hours they will give you the recorded videos. Minimum they want 4 to 5 hours to download and upload the videos. Right? So recorded videos are given. Class recorded videos are given. See that will be from morning. This Advanced PD they will inform you. This basic PD, it will be in the morning. Advanced PD admin will inform you. You can communicate with admin in the group or through this one. They will inform you. Class timing also. See, basic starts from tomorrow itself, from Monday. Basic starts from tomorrow. Basics. See, class recorded videos will be given and it is available for next 10 days. For example, today's class is available for next 10 days. After 10 days, it will refresh. Means for every day after class completing, you will be having a video, recorded video, whatever. For example, today you are not able to make for the classes. Today you are not able to make for the classes. Then you can watch the recorded videos after coming back. See, timing admin will inform you. In the group, admin will inform you. If people are in the WhatsApp group, right? If you fill that registration form, admin will inform you timings. Or you can come to the institute tomorrow morning. See, PD basics is happening only once in the morning. If you're not available, you can go to the recorded videos. Recorded videos are the current batch recording videos. Whatever the batch is running, right? From tomorrow, whatever the class starts, that recorded videos. It's not pre-recorded videos. Whatever currently, for example, tomorrow you cannot able to do the first, you cannot come for the session for some reasons, for health problem. Then that recorded videos you will get, that will be available for next 10 days. See, live support plus recorded videos both. Recorded videos is optional. If you want, you can use, or you don't. If you don't want, you cannot. You need not to use it. It's optional for you. If you attend live sessions, don't use the recorded videos. If live session you are not able to attend, then watch recorded video. Recorded video, it is a live session recorded video. Both is available. You can attend live session. It's online and offline both. Classes will have online and offline both. If you're coming to institute, that is also fine. If you're attending online, that is also fine. Both is available online and offline. So we will send the meeting link. You can join to the meeting. As how we are joining now, the same way you can join and you can take up the courses. Yes, for the lab, the tool will be installed in your laptops. So you can use from anywhere you want. It is not that you should come to the institute to use the lab. You can access the lab from your home only. It means you can use your tools from your home only. It's VPN. It's virtual private network we'll give. So you can access from wherever you want. But you should be having good internet facility, that's it. So tools will be installed in your laptop only. VPN will be given to your laptop. So from through VPN you can access our server and you can start working. See, when you enroll to the advanced course, right? From then the tools will be given. So advanced course, when you're enrolling, from that time the tools will be given to you. Everything will be hands-on. Nothing is done on theory. Whatever we have mentioned here, except this redact tool, right? We don't have redact tool for hands-on. Signing, so timing sign up, only this one. We don't have redact tool. Except this, everything will be hands-on. Whatever I mentioned here. Everything. So we will give two projects. One project will be done with the help of mentor. Another project you can do by your own. That reason only we have labs here, right? Labs is done for weekdays and weekend. That will be done with the help of mentor. All these steps. All the steps, whatever I mentioned, everything is hands-on. Except this redact tool. See, theory of IR drop will be done, but we don't have redact tool license. So redact tool using is not done. Because see, we don't have that much enrollment for redact. Simply we have to pay by huge amount for redact tool, but power analysis only few will register. Hardly 2 to 3 per year. So we are not renewed. We had earlier, but now we don't have. But theory will be covered on this one. See, advanced theory is only on weekend. Only theory on weekend. Labs will be on weekdays. Lab is more important, right? Theory is like what I thought now. Each and every topic. Lab is on weekdays. Even weekdays lab is available. Weekend lab is also available. You can opt anyone you want according to your comfort. See, all these things, weekdays lab and weekend lab will be done with help of mentor only. Mentor or trainer will be here or online for online students also. For every student, see, weekdays lab there will be timing. Mentor will join, students will join. Mentor will take through the flow, all the flow. For one project, mentor will take through the flow. Mentor will tell what step you have to do, what commands you have to use, how to use the tool. Everything mentor will do. Along with mentor, you will do it for one project. Second project you can do by your own because one project is already done.
So for the weekend lab also there will be some time.
Yes, so tool access is for everyone. It is for weekend, weekdays. It is not that the tool you are using only at the session time. You can use the tool 24/7, whenever you want. It's not the tool is working only during your working time or only during the lab hours. So tool you can use whatever time you want. See, lab is you can opt any lab you want. Both labs will be taken through all the flows. Here there is a separate mentor, here there is a separate mentor. Both the mentor will take through all the flows. That's it. So in weekdays we'll go, see weekdays we'll be having more enrollment. We'll go little bit slow because we have 20 students. For 20 students, we have to show all 20 students, we have to fix the violations. In weekends, hardly we'll be having 3 to 4 students. So it will be a little bit faster. Whatever we have done in 4 days, we can cover only in 2 days. But both same topics will be covered in weekdays and weekends both. And tool you can use whenever you want. It's not that tool you should use only when the session is there, right? You can use whenever you want. Tool is not only activated only in the during session time. You can use whenever you want for both the persons, weekend and weekdays and weekend. Yes, Ismail, you got it. Right? You can use tool whenever you want. It is not that you should use only in weekends or weekend. See, you can use a tool whenever you want, but session goes on one particular time only. that you will get the recorded videos. You can see recorded videos and you can do it. In your recorded videos we are giving, right? The recorded videos will be available for next 10 days. Today's class video will be available to you for next 10 days. We will give you the portal link for you to access videos. If you are not able to make in the particular timings, you can watch in the evening and you can do it. For every student, individual group will be created. WhatsApp individual group. Individual WhatsApp group will be created. You will be there, mentor will be there, our admin will be there, and some directors will be there of the institute. Any queries you have, you can post in that. Technical queries. You are not attending classes daily, for example. In between, you got some doubt. You can post in the means you cannot connect to the mentor, right? Because you're not connecting to the classes. You're watching only recorded videos. While watching recorded videos, you got doubt. Post in the individual WhatsApp group. So mentor will respond to you. You got doubt that I I am not able to get port placement. The mentor will respond you. See, port placement in detail is covered in next video. Please watch it.
Okay, understood. Yeah,
So
thank you.
we'll be having individual WhatsApp group for every student. Yes, please ask me what is your doubt online. Okay, then thank you. Any queries you can post in the group or you can contact the admin.